Okay, in this section of the lecture, we're going to be looking at affect subtyping. Why is that? Well, we actually want more expressive control structure in a real programming language. And we've used quite a simple one so far, just the lambda calculus, augmented with our reads and writes to named channels. But let's add something a little bit more interesting into the language. Let's add in an if then else, so that we can evaluate an expression 1, and then if it's true, evaluate E2, a second expression, or otherwise evaluate E3, which is a third expression. So we're always going to evaluate E1, but we might evaluate E2, or we might evaluate E3, depending on what the result is of our expression E1. Of course, we have to therefore create a rule to deal with this. So here's our rule. E1 is going to produce an integer that allows us to use it as a predicate to determine whether we're going to go left or right, whether we're going to take the then part or the else part of the condition. Then we have E2 has type T and E3 has type T. And we can say based on that, then of course, the result of this particular expression, this conditional expression, is of type T. We now have to add in our effects as well to make it into the type and effect system. And so, as before, we can assign the effects that will be seen to each of the expressions that are going to be evaluated. Let's say E1 has set of effects F, E2 has set of effects F prime, and E3 has set of effects F double prime. Then it's fairly simple to see that the result of evaluating all of these is that because E1 is definitely going to be evaluated, you're going to definitely have a set of effects F, but you may see effects F prime or F double prime, and the easiest thing to do in that case is just to say that all of them get seen. And so what we're going to do, we're obviously overestimating here, what we're going to do is union all of those sets together to get the effects that are seen through evaluation of this expression. Okay, that's relatively straightforward. But the kind of catch here, of course, is that there's some valid uses of this if then else, which we can't handle just by using this particular rule. Okay, let's look at this particular expression here. So we've got if x, then lambda x dot xi exclamation mark 3 dot x plus 1 else lambda x dot x plus 2. Okay, what can you see in this? The answer is that on the left-hand side, in the then part of the condition, there is a write to channel named xi. But in the right-hand side, there isn't any write. There's no read either. We're not doing anything with channels at all in the else part of this expression. You can see this part, of course, gets evaluated and judged to be of type int to int with no latent side effects at all. That seems fine so far. The then part, of course, where we're doing a write, gets judged to be int to int with latent effects, a write to this channel xi. Let's look at our conditional rule. We just developed this, so we know what it has already. But the issue here is looking at E2 has type T and E3 has type T as well. But we can clearly see here that the then part of this expression, the lambda x with the write to the channel, has latent effects w psi on the type, whereas there's no latent effects at all on the type for the else part. So in fact, these types do not match. They aren't both of type T. There's a mismatch because of the latent effects that we've embedded into the type system to actually capture the fact that they don't happen yet, but they happen on function application, and therefore this will not type correctly. Okay, but we really want it to. I mean, it would be silly if you had to write to a channel every single branch you took of an if then else statement, right? So we want to fix this up so that you don't have to write if you don't really want to. You're free to do things in the way you please. Okay, and we solve this problem by adding a new rule to handle subtyping. So our subtyping rule basically looks like this. We say that if we have an expression which is of type T to T prime with latent effects F prime and immediate effects captured in set F, and if we say that F prime is a subset of the set f double prime, then in fact what we can actually say is that expression E has type t to t prime with latent effects f double prime instead of f prime. So we're saying as long as the set of effects that we've seen is a smaller set of effects, it's a subset of a larger set that's otherwise there, then it's fine to use the larger set instead. Okay, and we add that sort of imprecision, if you like, into it to enable us to do this subtyping. Back to our original example here, we have these type judgments for the two functions that we've created, and on the right hand side we can clearly see that the int to int with no latent effects is a subset of int to int with a right inside it. Okay, and so because of that we can use our subtyping rule to in fact say that we'll treat the lambda x.x plus 2 as of type int to int with right to xi latent effects. Now of course these latent effects match, and therefore the whole expression matches, and we can consider these as equal and well typed based on the inference rules that we've got. So this information is very useful when deciding whether particular transformations are safe or not. An expression with no immediate side effects is referentially transparent and can be safely replaced with another expression with the same value and type, and no change to the semantics of the program. So of course, if you don't see any side effects from a particular expression, you are free to do far more transformations to it because you don't have any side effects that you need to preserve. Whereas if you have side effects in a particular expression, then, maybe you can still do some kinds of transformations to it, but you need to keep those side effects in order to maintain the semantics of the program. So, referentially transparent expressions could be removed if live variable analysis says they're dead, for example. And that would be, you could perhaps remove a function call and all of the computation that happens all the way down the call graph starting that function call if actually the result of that function call is never ever used. And that would be absolutely fine in a pure function where all of the sub-functions that are called are also pure and there's no side effects there, and our type judgment can tell us that. But if there's somewhere along there that has side effects, then perhaps we need to do some sort of different transformation to remove it, even though the result is never actually used. So for safety, we talked about the safety of the inference-based analysis before. And here, of course, we have the set of effects in F that we have to consider as well. And what we're just saying is here, essentially, that the set of values, the value that is produced by evaluating expression E and the set of effects that actually occur when you're executing it are both possible results that you could be seen from all of those that result from evaluating E. Now, what we've done so far is look at using sets of effects. Okay, so what we aren't doing is worrying about the order in which things occur. And that is fine for quite a lot of analyses. Often it's enough to know whether something has happened or not, and not necessarily how many times or in what order. But there are, of course, situations where you want to know what the order is. Okay, here, for example, let's look at these again. Okay, our set of effects were to read and write, read to xi and write to zeta. This one here is a read from xi and a write to zeta. And the third one, of course, is a read to xi and write to zeta. Okay, so all of these expressions, although they are substantially different from each other, as you can clearly see, they all have exactly the same set of effects that occur based on the system that we've developed so far in the lecture. Now, it might be that we actually want to keep a different representation of the effects so that we can keep track of what is actually happening. Maybe it really matters to us whether we have written to zeta before or after we have read from xi. We want to make sure that in all program paths the write happens second. Well, in this case, we actually couldn't capture that information. But by using a different representation, We don't have to use sets, of course. By using a different representation, we can keep track of more information and therefore make these judgments. So one option is to use sequences of effects and an append operation when combining them. So here was our read and write rules. And what we can do is actually transform the bottom, the underneath the line for each of those, so that we're not using set union and sets, but we're using sequences and appends instead. So you can see here we've changed that into the sequence containing a read to xi and then an append of the effects f. And for the write rule, we've said it's the set of effects f from E1 appended with the write to zeta and then appended with the set of effects that you see from executing E2, which is f prime. All the other rules you can transform in exactly the same way. And what's happened when I've written them in the slides, you'll see that the sets are unioned together in exactly the order that you need already. So it is simply a matter of taking those slides and looking at the rules and replacing the sets with sequences and the unions with appends instead. Everything else is exactly as it should be. The order has already been taken care of for you in those, although of course it didn't matter in any way when we were developing it earlier on. So now we've got those sequences, we can see that all of these have different effects. Okay, we can see that this first one obviously reads from xi and then writes to zeta. The second one, we can now see it writes to zeta before it reads from xi. And the third one, of course, writes to zeta, reads from xi, and writes to zeta again. Now, of course, whether we use these new sequences or whether we use sets depends upon what we care about and what we're actually trying to infer. As I said before, it may be the case that we actually don't really care too much about what ordering we have or the number of times we do something. We just want to know whether something has happened or not, or we just want to capture that there are side effects rather than what exactly those side effects are. And as ever, you can make the analysis more precise by using the sequences or less precise. And if it's less precise, keeping less information around, it will be using less memory when you're actually doing the analysis and perhaps run a little bit faster as well. Okay. So it's up to you. In the channel example, we didn't care too much, but if we were tracking file accesses, then of course it would be important to worry about whether reads or writes happened after a file had been closed. And memory allocation, of course, is a big problem in languages like C. We'd want to make sure that no block of memory got deallocated twice, because that would be a double free, and therefore that would be a very bad thing to happen. Right. So to summarize this lecture, okay, we built on our inference-based analysis from the last lecture. We essentially augmented our inference-based analysis for type systems with sets of effects. Now, these effects captured the side effects that occur when expressions are evaluated. We had to treat our functions, our lambda abstractions, in a special way so as to capture the fact that effects don't happen when those expressions are created, when the lambda abstraction is created. It actually happens on application of the functions. So we have to change the type system itself so that we annotate the type of the function with the latent effects that actually happen. Then we can, of course, modify our type system to produce judgments about both the types and effects that are going to be seen from evaluating particular expressions. We had a little bit of a problem when we introduced a conditional where one expression may be evaluated or another one, and we didn't want their types to actually have to match exactly, because otherwise we'd be very restricted in what we could do. So what we do is we in fact add in subtyping to handle these types. And of course, right at the end, I've just showed you the fact that we don't need to use sets if we want to keep more information around as we're analyzing our program. And actually we can use sequences with an append operator or some other system to actually make sure that we keep around as much information, but ideally no more than what we need for the particular use case we have for our analysis. Next lecture, the bonus lecture 13a, is going to be on alias analysis and points to analysis.